Hello everyone, and welcome again to our Inaccuracy research group at NUS. We're very excited to share our new body-driven voltage reference, allowing reliable operation under an unregulated supply, widely ranging from 0.6 to 1.6 volts for voltage regulation suppression in purely harvested systems, while pushing power down to tens of picowatts. Now we will watch Luigi's presentation and the chip demonstration.
Hello everyone, this is the test chip that we designed in the 180 nanometer technology. The temperature sensor comprises a first stage performing temperature to voltage conversion and a second stage to convert voltage to frequency. The first stage drives the body of transistor into subsequent oscillator, which in turn perform voltage to frequency conversion. Frequency to digital conversion is finally achieved by simply counting the transition of one oscillator with the other one. The two ultra-low power oscillators are implemented in the dual mode logic previously introduced by our tool, and their frequency is controlled through the body terminal of the footer of the transistor in the dual mode logic. The body-driven ring oscillator keep the power in the tens of picowatt range, improving linearity compared to conventional gate voltage control, and avoiding the challenge of accurate generating of peak ampere current with controlled temperature coefficient in the conventional current started ring oscillator. The temperature readout is performed by a fast and slow oscillator, respectively driven by a proportional to temperature and a complementary to temperature voltage through the body of their footer transistor. When the temperature increases, the frequency of the two oscillators diverge nearly linearly. The frequencies are then converted to digital by counting the oscillation of the fast oscillator in a time window defined by the slow oscillator. The counter is based on a dual-edge triggered flip-flop to double the count for a given window value, improving the resolution of the temperature sensor without increasing the conversion time. At the lowest power consumption of 38.4 picowatt at room temperature, the resolution is 0.5 degrees Celsius from -10 to 70 degrees Celsius, and the conversion time is expectedly long due to the low power. Multi-die measurements across all corner wafer are presented for completeness. The worst case error is radar consistent across process corner, and it ranges from -2.2 degrees Celsius to 3.4 degrees Celsius in the worst case across all corners.
This design reduces the power to the lowest level reported to date by at least 3 times. The less than 40 picowatt power fits the power budget of millimeter scale harvesters at most practical environmental conditions. This allows uninterrupted, which means always on, operation, even if solely powered by a millimeter sized harvester, for application with relaxed conversion times such as pharmaceutical temperature monitoring, environmental monitoring, and food cold chain monitoring. This also enables a new class of temperature sensors that are always on and yet simultaneously purely harvested. The suppression of voltage regulation preserves the power reductions at the system level, and the elimination of the battery makes the proposed sensors suitable for green and environmentally friendly silicon systems. Thank you for watching. Feel free to explore more in our Green AC website.